everyone. For those of you joining the session, welcome to this month's C4AI AI Tech Governance webinar. We'll just give everyone the usual minute or so while they join the Zoom. I'm really excited for this session today, and I hope you all are too. I can see lots of people trickling into the session, so we'll maybe give it another 20 seconds of me vamping like this, and then I'll get into the proper intro once everyone's joined. Loads of names a few names I recognize from previous sessions and some new ones as well. So this is really fantastic. Thank you everyone for joining. And you know what, I think we have enough people for me to start the official intro. So hello everyone, and welcome to this edition of our Tech Governance webinar series at C4AI. I'm Aidan Pepin, and I'm the Policy and Responsible AI lead here. For those of you who don't know Cohere for AI, we are Cohere's nonprofit research lab, and we support fundamental research on machine learning through open science approaches. And through all of our work, we get to engage in a range of conversations that aren't only relevant to the technical research around AI, but the governance of AI as well. And we get to do those conversations with deep domain experts. So this webinar series is our effort to bring those conversations to a broader audience. This month, we're focusing on the energy and climate and financial and infrastructure impacts of AI technologies and how the efficiency of models, among other things, might be one route to addressing and exploring some of those issues. So to discuss all of this, I'm joined by the four fantastic people on your screen. We have Dr. Sasha Luccioni, who is the climate lead at Hugging Face, who, in addition to a range of key research publications on AI and energy, she recently published a policy primer on the environmental impacts of AI with some colleagues. Highly recommend you all to check that out. We have Deval Pandya, who is VP of AI Engineering at the Vector Institute in Canada, prior key roles on energy and digital tech at Shell's Future Energy Network, Mojo Global, which is a non-profit developing open source software for greenhouse gas accounting, and the UN Economic Commission of Europe. We had David Kanter, who is founder, board member, and the head of ML performance at MLCommons, where he leads performance benchmarks work. He's previously been at Intel, Nvidia, Qualcomm, Microsoft, and many others. And MLCommons recently released a new performance benchmark, which has implications for, among other things, measuring energy impacts of models. So I'm excited to hear more about that, David. And of course, we have Sarah Hooker, who's VP Research at Cohere, the head of Cohere for AI, and leads our technical research efforts across a whole range of topics, multilingual, evals, and of course, model efficiency. She's also my boss, so I'm grateful to her for giving her time to our session today. We also should mention, of course, those of you that are paying attention to the Time 100 list, you'll recognize Sasha and Sarah as being named in that. So we're super excited, and kudos to them both for being recognized for their great work. So that's enough preamble from me. We're going to dive into some questions and explore this topic. We do have the Q&A function, which I'll keep an eye on throughout the session as we go. So if you in the audience have questions, please drop them into the Q&A and I'll pick them up and ask our brilliant panelists. But without much further ado, I think let's get into it. And I really kind of want to start by setting out the scene here. You know, what is this issue that we're talking about, the energy, infrastructural, climate costs, and so on associated with AI models? What's the scale of the problem we're tackling with here? And I wonder if, Sasha, I realize I didn't pre-warn you about this, but I might come to you first, if that's okay, seeing as you've recently published some work on this topic to kick us off, and then I'll come to the others on the panel as we go.
That's a tough question to start with. I think the main problem is that we don't have the high level numbers. We have numbers about data centers in general. And so also people go back and forth about this, but I think it's around 3% of energy use. But this is data centers that run everything from streaming to email to anything that would require compute. And so what portion of that is AI is kind of under debate. It also depends on what you want to include or not. And to add to that is the thing is that AI is also often embedded in different things, right? So it's not typically when people are counting things or trying to understand like agriculture or transportation, right? They make these categories, these verticals typically, and then AI doesn't really fit into any of the verticals. So I've heard a lot of back and forth about like, where do we even put it? Do we put it in ICT with cell phones? And so yeah, so I guess the long and short of it is that it's hard to say exactly.
Yeah. Just to amplify that, which is a really great point. You know, whenever people ask me about the difference between training and inference, One of the things I like to say is for those of you who cook in the audience, I really enjoy cooking. Inference is like salt. There's not a lot of people that just sit down and eat salt. But, pick your favorite dish and you add a bit of salt and it gets so much better, right? And so, that holds for a lot of computing workloads where, maybe 10 years ago, we would stitch together a bunch of APIs and call it a web app. But now there's a lot of inference load in that. And, as Sasha pointed out, we might be doing inference with a tractor that's helping us harvest food, right? And then how does that show up? And training, right, is much more discrete. It's a very dedicated workload with very dedicated systems and kind of easier in some sense to keep your eye on. And so there's definitely this training inference discrepancy where the inference is really starting to take off.
Yeah, I'll just add like a couple of things there. Like Sasha, maybe like, so we don't know how to attribute how much of the data center is AI, but isn't everything going to be AI, like, or majority of it is going to be AI in the future? Like we are seeing this trend, like, where it's becoming like very difficult, even like normal applications, everyone is embedding AI in it, right? And so there is this thing where most of the applications will have some form of like models behind them, like powering them, right, kind of thing. So that is one trend. The other thing, which is also, I feel like worth mentioning, is that while it is say 1 to 3% today, it's increasing, or it's projected to increase by 20 to 30%, somewhere between that. Like, so that is also like worrisome in terms of how we meet those energy demands. And then third is, which is a positive thing, I feel, and I think you mentioned it backstage very briefly, but I would like to highlight for this audience is say, while 1 to 3% seems a lot in terms of like global energy demand, the greenhouse gas associated with them is quite less comparable to other sectors. For example, transport, like air transport, right? Air transport is around like 1.5%, but the GHG emissions is like way higher from the 1.5% that they consume versus say data centers. In some sense, like it's almost half of it, right? And so there's also this opportunity that while we are scaling this data center infrastructure, we can still, along with that, expedite the energy transition to cleaner grid.
Yeah.
Sarah, do you want to come in? Yeah.
No, I was just going to kind of go back to the original premise, which is why are we all here? I think, Deval, you were kind of touching on it, which is that despite the kind of formidable technical problems ahead of us, like how do we measure making the differences between training and inference just constraints, but also how do we reduce that load are quite different. But I think we're here because a lot of the trend is upwards, but like rapidly upwards, and also because of the type of workload that this is, right? So, things like flight overhead or agriculture are very specific. This connects directly to our utility grids. And so the strain is much more immediate and pronounced because it's both producing like a energy output, which may be smaller than those other industries, but it's directly taxing our utility grids. And so I think it's really interesting to think about in that frame, like the urgency of why we're here and why there's so much work on this. And Deval, you're kind of hitting on that when you talk about this like rapid growth that we've just seen in the last few years. I do think that it's interesting to think about how to put this in a taxonomy. I agree with Sasha. It's kind of hard when, even agriculture is fueled by more and more AI. So it's kind of interesting to think about that tension. But those questions are there because it feels very immediate.
So I guess one of the other things you said, Deval, which I thought was interesting, this kind of AI is embedded in everything. It's going to be increasingly embedded in everything. And the points that I think you were making, David, as well around inference, we have some questions around if the increasing scale of these kind of technologies and technologies that are based on AI models is trending upwards, as you say, Sarah. How do we kind of tackle some of the things that might come along with that? Does that mean trending upwards of the, we're talking about the data center percentages in terms of AI demand being relatively small compared to elsewhere, but if the trend is upwards and if the trend is maybe sideways as well in terms of where these technologies are deployed, then those numbers might increase. So I'm wondering kind of how do we tackle that problem? And it's not just about the training, but it's about the deployment of these AI models across a range of technologies as well. What are some of the things that we can do in terms of the efficiency gains that may come, for example, with models? I'm curious if there are thoughts there on that.
Well, I would just add one other point to actually sort of that I think is really interesting, and actually, some of us were on a panel about this yesterday with the OECD. One of the things that we see in terms of sort of dislocations and sort of the design of processors for AI is that they're on a very rapid trajectory to increase the power consumed per processor and make them more powerful. And in some cases, that means our existing data center infrastructure won't work, right? Which is very challenging. But the good news, right? And that sounds bad on the face of it. The good news is that next generation of technology is intrinsically more efficient, right? But the challenge is, if you're moving from, say, a 500-watt processor to a 1,000-watt processor or beyond, or if you have to go from air cooling to water cooling, that creates a lot of change. But one of the positives for me is, it's really beginning to get people very, very focused on energy as a first-order constraint, right? And one of the things I love about the community that we're part of is once there's sort of alignment on these problems, then you kind of unlock everyone's creativity to tackle it. And then, it doesn't happen immediately, but I like to think of MLPerf as an example of that. When we got good standards for measurement, we were able to drive the performance and capabilities for training by 50x over 5 years. And so, I think the question is, okay, what are the next things that will give us 50x in energy efficiency over 5 years? And anyway, Sasha has produced some great tools that make this really accessible, more accessible to software developers than I think it was previously. And there's also a lot of things we can do in the infrastructure level. So,
David, you've not only read my mind, but done my role of moderating there, because I was going to
sorry,
your direction, Sasha, next, because it was making me think of exactly some of the things here are the tools that we need to measure these things. And Sasha, you've done so much work there, so I wonder if you can share some thoughts.
Yeah, I think that we are still gathering information, and one of the tools that I helped create, which is called Carbon, is it's essentially a Python package that runs in parallel to any kind of code, not only machine learning, but that essentially measures the energy usage of the code, and based on how that energy is being generated, so essentially based on where it's coming from, it will give you an estimate of the carbon emissions as well. And I think it's relatively popular, and then when people track their emissions and they report them, then we can get a better idea of different types of models, different scales as well of training. And I think that that's really an important piece of the puzzle, like to just get an idea of what's out there. And another project that I'm working on now and with Sarah is to develop kind of efficiency ratings for AI models for the users. Like even if you're not training models yourself, even if you're just kind of selecting models or integrating them as part of a pipeline, for example, knowing what the relative efficiency of a given model is compared to other models of that category, I think is really important, because for most people, whatever, 10 watts per query or whatever, it doesn't mean anything. It's really quite abstract, but if you give them kind of like a range or relative positioning of a model, I think it really speaks to them a little bit more. And we have this for Apple appliances, right? Like and cars and apartment buildings in some countries. And so I think that AI is kind of can be one of those categories that we have these scores for.
And one of the things I actually really love about Carbon is it's much more universal and easy to apply. Like, one of the things I kicked off and am just like thrilled about it at MLCommons is we did MLPerf Power, which allows you to get, real system measurements for training or inference. And actually Aidan, in the introduction, one of the things you mentioned is the last round of training, we actually finally were able to deploy a methodology that allows you to measure in CSP data centers for training of models including things like our GPT-3 benchmark. And so, I think one of the things that's great is, to me, the MLPerf power is extremely high precision. And because it will incorporate all the hardware you're on, like what is the drivers that you have, what is the libraries you have underneath, and how can they, in a very significant way, improve efficiency. But it's, you have to actually do the measurement. And, I think one of the really great things to me about Code Carbon is it's a much broader based tool that allows developers to get an instinct for, I'm going to integrate this thing in. What's the potential cost? And is there something better I can use? And it's just like a lot more tools like this, I think, will really help point us all in the right direction.
I totally agree. I think that the development of these kinds of new tools that people can use to understand the efficiency to test, explore it are going to be crucial. One of the other things I think that's as important, obviously, is then the techniques that these tools help us to, or rather how these tools help us identify which techniques can help us increase the scores on these relevant tools or reduce the energy demands and get efficiency gains, essentially. So I'm curious to turn the conversation in that direction. What are the approaches that we're seeing that you're all excited about in terms of improving the efficiency of AI models, from whether it's at the hardware stack right the way through training, inference, deployment, and so on? Sarah, I know you have a lot of thoughts about this because we've talked about it, so I wonder if I can turn the question to you a little first. You're on mute, Sarah.
I think it's good to maybe take a step back. I think what's nice is, yeah, this challenge of whenever you have a challenge, it's nice to think about how we're measuring progress, which I think both David and Sasha, and even our work, our collaboration, Sasha, has thought about a lot. How do we communicate progress? How do we actually make a dent is a separate question. And maybe I'll back out just for everyone who's listening. I think that there's almost two stages we typically do this. One is when we're building, there's so many comments right now in our webinar chat commending David's analogy. I feel like I want to go for it too. So let's see how this goes. But one's when we're kind of building the house, and then the other is like a renovation afterwards. And so the building the house is when we're training the model. What can we do with efficiency? I think here we're seeing super interesting trends where we are seeing much smaller, higher performant models. Like some of the biggest axes have been using synthetic high quality data, distillation, understanding like how we train using much more nimble, smaller models, typically relying on one big model to kind of steer. And then we have, let's say you built the house, you built a huge house, and now you have to somehow renovate it to get it into a smaller plot. And so you hack away the columns. That's basically our post-training techniques. We do a lot of quantization, sparsity. We do some cascading, like routing. So this is where you can route to different models depending on the difficulty. But what I will say is this, is that a lot of what you do once you have a model is acrobatics to get it smaller. Here's where it gets fun, is that it's kind of, this was alluded to earlier in our conversations about, how tricky it is to measure. And I think David was the one who said, well, training is much more kind of fixed. It's in one place. So once you serve a model, it just scales. So you have a lot more instances of a model because you spin different ones up depending on people fine tuning. And so serving and how you do that is super interesting from an efficiency perspective. Even how you batch requests has a massive impact. And so this is something which sometimes gets lost in the details, because I think for good reason, we're measuring a lot of training properties first, because this is much more contained. We can look at a single model, but inference, I think, is where the meat of the challenge is. How do we both minimize that cost as well as how do we track it? But yeah, let me open up. I think, Deval, do you want to weigh in here?
Yeah, no, I think there is, I feel like, okay, I'll step back a little bit, and maybe you mentioned, Aiden, about like hardware and the model, and Sarah, you touched on model, and Sasha, you're doing a lot of work on like monitoring. I actually agree that you cannot manage what you don't monitor. So I think the first step is like you have to monitor these things. maybe I'll share something from the other side of the equation is on the energy side of things, right? And I feel like there's a lot of, you mentioned like policy people here, so I'm not sure if there are like energy policy, energy markets folks here, but just a month ago, PJM, which is the largest grid operator in the US on the Northeast, and they had their auctions for base capacity load. This is the amount of electricity which we have to provide irrespective of what happens. Like, this is the minimum 365, 24 hours. You have to do that. The base capacity load auctions cleared at 800% higher than last year. And which sent like my bunch of Slack channels and WhatsApp were going bonkers when this was happening live, because this is like unheard of. And why this is relevant to us is this is the grid where Data Center Valley in Virginia sits in, right, kind of thing. And so the opportunity here, so when I look back at how like the grid was operating and how it is transitioning to like more cleaner grid, there's a lot of parallels between how we are operating like ML systems today and what could be the future. And so currently what we are seeing is a trend moving away from the segregated model where you build this large power plant, it's supplying like this electricity to like thousands, hundreds of thousands of households and industries, which is what is happening for the most part today. We have these large models which are consuming like huge amount of energy, and now that they are being embedded in different forms through different like downstream kind of tasks, but also like distillations and all of the things that you mentioned. The big part of the energy transition is how do we distribute this grid away, right? So can we actually have distributed computing as a parallel for this? And what happens when we don't have, I don't know, like 30, 100, 200, 300 megawatt hour data centers, but when we have 5 like megawatt hour, 10 megawatt, but bunch of them in different parts of the electricity node. And there's a paper which came out very recently by Meta, and which I think is a good, this is the first time I saw someone deliberately like present this. It's called MAST. It's about like scheduling of ML workloads with geo-shifting and time shifting. And when you combine that with geo-shifting and time shifting for energy grid balancing, I think there's a huge opportunity to actually increase the amount of energy that we are consuming for ML workloads, both training and inference, while decreasing or keeping the relatively like the energy greenhouse gas footprint, right? So I think one of the other things which let's not get too bogged down into how much like kilowatt hours we are consuming, but what is like the greenhouse gas implications of it is actually more important, at least in my mind, and how these electrons are being produced, right? Let's say we increase it by 100x and all of those electrons are produced by renewable energy. I think it's a bigger win, actually. And I'll just finish by saying this, like there's another huge parallel in training and inference. And so when you think of training, this is like, say, a small period of times, few months, few weeks at max, even for the large, like really large training jobs, but you're operating at this peak, right? And we are consuming everything. This is very much relevant to what grid is designed for. They call it like peak load, right? So you don't design your grid infrastructure for, say, what is an average. You design for that one, say, in Texas, you would probably say design for that one day in summer where it's going to hit like 110 degrees Fahrenheit. And so everyone is blasting their ACs and everything. So you're designing the entire grid for that one thing. And that is what's happening in data centers, like at least the newer like training data centers. You're designing this and you're collecting all of this like chips and infrastructure and concrete and steel for very like to cater to this very short period of time of like really large training runs. And we have to slowly but definitely like move away from it in terms of how we can distribute it like across time and across geolocations, which I think is a huge opportunity of tackling this from the energy side.
I mean, I think one of the things is actually, I mean, I suspect for a lot of training stuff, it's actually pretty heavy duty cycle, like, always training, especially if we look at some of the bigger ones. But I think one of the things that's actually very promising that you point to is we've all said, inference, if we were to make the analogy, training is compiling the code, inference is running it. And, one of the great things is, I'm seeing, and probably a lot of other folks are seeing, a push for many things to go to endpoint devices, right? Whether it's for connectivity or privacy reasons. And, that does have the effect, as you say, of like sort of distributing it out, right? If we can run our models locally instead of a data center. And, I guess one of the questions is that also gives us, the silicon architect in my mind says that also gives me a lot more silicon to throw at the problem. right? You know, we can get our MATML engines in every PC or every smartphone. And yeah, what does it take to help get us there? But actually, one of the things that you mentioned of sort of the co-location of energy and data centers is actually making me think of the you know, the data center as a computer, right? By the late Luis Barroso, but sort of how can we apply like truly big systems thinking where the system incorporates the grid?
The only difficulty with that, I'll just point out, because I think it's a lovely dream, David, that everything is local. But just for
Not
framing
everything.
to everyone here, it's very formidable as a problem, particularly edge devices are not GPU optimized, like our current workloads. It's just very taxing to get the right performance. So I
Yeah.
agree. It holds the same appeal of a dream for me as totally decentralized, shared compute, even for training. But in practice, we still have some work to do because it's a formidable workload. But I agree, it's interesting. I do think this idea also of co-locating data centers, just to point out why we don't do it. Typically, data centers are significant really infrastructure investment, and they're often co-located with populations that are of commercial interest, which is why we have like 0 data centers in some parts of the world. I think particularly Africa, Latin America stands out as having very limited data center serving, and you can kind of see where they are in the continent, and they're very oddly placed. So many users in, for example, West Africa end up using data centers in Europe rather than using data centers in Africa. And this is typically a combination because data centers like infrastructure tend to be very tied with political and economic decision making, which Deval was speaking to, this idea of, you know, all these energy utilities are managed in different ways, which makes treating it like a optimization problem formidable, even though I think that's the way we should go. Because I love Deval's vision of, well, the same way that we've shown that algorithms can really help optimize data center specific usage, we could think of this as, you know, a problem where it's an allocation problem, and how do we best optimize? The difficulty tends to be that these are very entrenched in a kind of in the US state choices, but I agree there's very interesting problems there for optimization. It tends to be done on a state-by-state basis because every state has its own set of protocols about energy, but this is still promising. But just to share to everyone why we're not currently doing these things.
Yeah, no, yeah. Distributed training, to be clear,
Is even
maybe
harder. Yeah.
yeah, that's currently you know, mostly science fiction. Yeah, I think the hope is maybe on the inference side and
Yeah.
only some workloads, right? That's I think the another good gradation to maybe introduce is, you know, some things where like recommendation, I think becomes relatively more challenging to do at the edge because there's this natural gravity towards the data, right? Yeah, whereas, you know, if you want like the idea of everyone having a chat bot on an edge device, maybe one day if we get big enough and more powerful edge devices, or
Yeah.
conversely small enough models, or if we co-design the two, right? So there's
So just what David's
yeah.
talking about for those in the audience. So David's talking about the cost of sending data back and forth. So like, let's say that you need data for your model. Even if your data is local, then you spend a ton of time still getting data from somewhere else. I like to make the analogy. So my parents recently retired and they're obsessed with birds. So bird identification is something that can definitely be local because birds don't change drastically overnight. And so you could probably have your data local and your classification model. But something, and David's mentioning recommendations, something which you really need up-to-date data because you want to take into account what is the inventory or things like that. That's way trickier to do local. So, but yeah, super fun.
I'm going to take this quick opportunity to remind folks in the audience we have the Q&A function on Zoom. If you have questions that you want to ask, please drop them in there and we'll get round to them. Meantime, I wanted to loop back to a point that I think, Sarah, you introduced by talking about the different geographic, I guess, geographic, geopolitical, geoeconomic questions here around why certain data centers and certain resources exist where they do. And it made me think of another aspect of this topic, which is around kind of I guess the access to the resources needed to make use of these models, to innovate with them, to develop models, to deploy them in local systems. And that feels like another big part of this conversation, whereby not only is it currently a huge barrier because of where the resources are located and who has access to them, but sort of some of the potential things we've been talking about in terms of solutions and ways to address those challenges don't just have implications for energy demand and thus climate impacts, but also have implications for reducing the resource need to be able to make use of these technologies. So, I mean, Sasha, I can see you nodding away there. I don't know if you have some reflections to come in on that, but I think it's a really interesting part of this conversation as well that is worth bringing in.
Yeah, I agree. I mean, I've been thinking about this a lot as part of the ML, like machine learning and society team at Hugging Face. Like I work a lot with people who are coming from an ethics background or a philosophy background, and we talk a lot about the fact that, for example, so I came to work at Hugging Face because I'm a big fan of like sharing and recycling and the circular economy. So for me, like the hub is an example of that. People upload models and share models, and it's no one needs to train from scratch or you know, like spend time looking for what they need. And for me as a hippie, it was like that's the way to go. And I think that all of these questions of accessibility and democratization, like it goes above and beyond. I mean, climate impacts or efficiency, but it really has to do a lot with, you know, if someone trains a model and spends those resources and then puts it up, I mean, anywhere and shares it with the world, then you can keep building upon it. And you like the barrier to entry is lower. You don't need to train a model from scratch. And I was actually, I've been working on a paper about this with some colleagues from the DARE Research Institute about how actually things like equity and accessibility are actually linked in terms of sustainability and ethics. And I find that it's really interesting because often these conversations are not had. Like I see a lot of workshops about specifically like efficient machine learning, and then other like there are entire conferences dedicated now to ethics and, you know, and equity and things like that. But the nexus of these two topics is actually really important. And when you start thinking about it, you're like, well, actually, you know, efficient models are probably more equitable because, you know, you need less compute, less money to run them, et cetera, et cetera. And so, I mean, this is a topic I think a lot about essentially. So Sarah,
Yeah,
what you're doing at Cohere for AI and the Scholar program is actually great for the planet.
again, you're all doing my job of moderating for me, because I was going to make that same link of Sarah. I feel like, yeah, this is very important to us, right, in terms of the Scholar program, in terms of the work we've done on IA. I don't know if you want to speak to some of this as well, and how some of our current thinking on efficiency feeds into this part of the issue as well.
Yeah, I think so. I think what Sasha said is super an important axis of this, right? So we've also introduced models and released models, particularly with a goal in mind. Probably the most important was Aya, which also was an effort to make sure that the creation of the model was also shared. So you're building not just access in terms of access to a powerful model, but also you're creating a community of researchers at the same time. So it's creating the technical capacity, which is a very important component of this. I will say, maybe because this is a fun setting to share this in and think about this in, I have been grappling with whether releasing model weights is enough. And here's why. We've released pretty big model weights. So this is part of our commitment to access. Like we've released up to 103 billion. No developer is running a 103 billion parameter model. And so it may be available, but is it usable? And one of the reasons, one of our immediate actions following that was to release AP models. So we really wanted to release much more compact models. But even that, to do work on a fine-tuned AP, you definitely need a GPU. It would be really painful to do without. So I think there's another axis to this, which is compute and access. And it's really interesting to think about. I often think about Google Colab as a super powerful and often underappreciated axis in this direction. Like how many of the people who apply, we run the Scholars program as Ada mentioned, we use Google Colab for take home because it's the one thing that can guarantee that everyone has access to, let's say, a fairly unreliable GPU access. Let's not, but it's really, if you think about that in the global sense, that's really impressive, right? And so we've also started our own compute program with that in mind, like giving compute grants, but it's really a band-aid, I would describe, to this wider problem of how do we create more nimble infrastructure. there, I just want to, because again, this is a fun audience to do this with, because, thinking about a policy perspective, I would say a lot of different national governments are thinking about this right now, where like, what is our national policy around access to compute? I would say I see the same mistakes being made again and again. So I'm going to share my grumpy takes right now because I think this is more fun for the setting. One is the idea that it should be hosted by a university consortium. I think history tells us that typically the difficulties there is it ends up in a narrow network, and that the biggest issues with compute infrastructure is that if you go the route of building your own infrastructure, you have to maintain it. And also you're kind of locked in. So your infrastructure is only available. One of the biggest benefits of successful infrastructure is nimble access. So when there's availability, you have some way of scheduling compute. I will say universities are a good medium to do this in, but you just have to think about what are your mechanisms for making sure scheduling happens easily. In the EU, there's a big issue where people have to spend a long time getting grants and then they're allocated grants. But the process itself takes so long. These ideas, our field is moving very fast. So for national policy, I think really emphasizing that there has to be some room for independent researchers, people outside of university systems, but also that you probably want a mix of compute resources. And so you can build your national infrastructure, but that's probably one of the most time-consuming routes to take. But I'm curious, maybe actually, Deval, have you been thinking about this? I know you must be to
A
some
lot.
extent. Yeah.
Yeah. I mean, for folks who are here from Canada, so like we have been involved in a lot of advisory work, working closely with like our government partners in actually how to think about this, right, in terms of national infrastructure. So I'll give like a vector hat answer, and then I'll probably give like my personal kind of opinion as well. So I do think that it is becoming important to have some sort of a national compute kind of strategy, mainly because if we think that the future, and we know the future is being built from digital infrastructure, so then we have to approach this. If you're a nation, you have to approach this in terms of the railroads and the highways that you have built. Like, this will become the backbone of the digital economy. And so there is a need for doing that. What is the right model in terms of, say, how we do that, which brings accessibility and agility together? At the same time, I feel there is a need, as you mentioned, like Sarah, about enabling access, but enabling equitable access, right? And then there's a big question about what should and should not taxpayers like pay for, right? In this. And so with that in mind, I feel I think like when we look like in the history of even and David, I remember like the very first conversation I had, we were talking about like the silicon like in the 60s and 70s and 80s, right, kind of thing. And there is a role for the government to play to enable innovation and provide that foundational infrastructure. And then there is a role for a public-private partnership somewhere in the middle. And then there's a role for like private companies to like take it and scale it and create like the economic value, right? So it has to be a continuum, and it doesn't have to be like one or the other. But to bootstrap it, like there will be nations who will want to have this infrastructure, which are not currently, and by infrastructure, I mean the data infrastructure and the data centers and the compute infrastructure, which are not 100% controlled by just for-profit like entities. And I do think that is where the sentiment is going. And the reason for that, which I agree on, is to create like more equitable, non-economic incentive, right? To do actual like science, to do actual level the playing field for like SMEs, right? In Canada, we have like a very interesting challenge because majority of Canadian productivity comes from small and medium enterprises. More than 60% of people in Canada are employed by small and medium enterprises, right? But so how do we balance that, right? But still not get bogged down into. I'll share my frustration. Like so, in Vector, we have our own cluster. We use Slurm, right? And Slurm is great. It's very robust, right? But from if you ask my team, like everyone would say, like we should have something better than Slurm, right? For scheduling and everything, like kind of thing. So how do we balance questions like this? And so that's one. Now, I think my personal opinion on this whole idea of having, this is not like a vector opinion, but my personal opinion that there's this huge sentiment growing across the world not just in terms of AI or data, about like being introspective about what it means for my country, right, kind of thing. And so there's like sovereign like data is picking up, right? And so I feel that there are dangers to that sentiment, because that will actually create a geopolitical world where we are imploding rather than collaborating. And so that is a huge challenge, right? And so we have to be very careful that within this sovereign approach, how are we forming the right partnerships, and how are we actually creating like collaborations which will benefit everyone? And we are not repeating the mistakes where we are leaving the global south behind, right, for example, or where we are actually creating like disproportionate like technological influence just in one part of like even like the modern world, right, kind of thing. And so how to distribute that power within the technological landscape geopolitically is going to be important. And this sentiment of sovereign compute is sometimes I feel like an antithesis to global collaboration, right, in its form. And I'll just finish by saying this, like tying it back to energy, right? So I actually, we talked about like all the challenges. I talked about the challenges on the grid and how this grid is like stressed and how we don't have enough renewable energy. I'll give you an example. If the entire world agrees that they will start building data centers in the Middle East and sub-Saharan Africa, we will not have any problem with greenhouse gases related to the data center growth. They have 364 days of sunshine. And some of the cheapest solar auctions, PPA auctions in the world are happening in that region, right? And so the challenge there is building this trust amongst nations to share this infrastructure, right? And that's not a technical problem to solve, actually.
So actually, there's a couple things I wanted to hop in on and play around with, because like I remember actually a great conversation I had with Garth Gibson a while back, and Vector actually made a very interesting decision in some of its compute purchases that I think it's like great to share with the audience, which is Garth and I were in a group together. I think Sasha was part of this, and there were a lot of folks who were thinking, how can I build the biggest AI supercomputer to enable the next foundation model? And Garth brought up this point that at Vector, they looked at that and they said, actually, what we really want to do, and maybe partially because of the SME focus that you mentioned, Deval, was not build a big supercomputer, but instead get a single GPU on the desk of every researcher, thousands of them, because that was going to give everyone the ability to play a bit, and it was going to train the next generation up in some of those skills. And the other thing, which I think is really beautiful, because it's important to think about, it's very easy to get wrapped up in the biggest and the best, while, neglecting, as Sasha and Sarah have said, some of the smaller stuff. But you also need data to go with that compute as well, right? My sort of napkin math for AI, if I ever get to give a TED talk, is sort of big data plus big model plus big compute equals innovation, right? And that scales at all levels. But right, if we want to give folks a lot of compute, we should make sure that they have useful and relevant data, which is, why a lot of the work, that Cohere has done around language and diversity is like really great. So.
Yeah, I just want to say a cheeky aside. Wait, Sasha, did you want to weigh in here? Okay, I wanted to say a cheeky note though, but David, while that's lovely, I do think for a grad student who wants to participate in breakthroughs, and actually probably Deval, your current setup is a bit different than that, I'm imagining.
Yeah.
Yeah, but I do want to say sometimes there is this idea of we should just emphasize equity, but actually for compute, the most efficient use of compute is where you have a nimble, concentrated cluster and some good way of allocation, because no one uses compute all the time. And so your most important ingredient, but I do agree, this idea of giving starter compute, which is why I think things like, Colab are so important. But for top tier institutions, they have to be given the compute to play at the highest levels. And so that is critical. Yeah.
I totally agree with that. Yeah, there's
I'll just add, like, so
yeah.
yes, our compute currently looks slightly different, like, or
I
quite a
would
bit
hope
different,
so.
different than that. But at the same time, I'll just emphasize that equity is not equality, right? So we are not talking about saying like everyone gets like, say, researchers who are doing fundamental math research get the same amount of compute who are doing scaling laws research, right? Like that is not what I mean by equity, that kind of thing. And I do agree that while we need to have like better allocation systems and all of that is relevant, there's also realities that even forget about just vector, but even large nations will not be able to compete at the scale of where building a 350,000 GPU cluster, right? Like that is not, first of all, even if they can, I don't think they should. Like, there is not this is what I meant by taxpayer money. This is not the best use of taxpayer money, right? Kind of thing. And so how do you create competitive advantage in this landscape is through everything which is not building the largest model, right? Kind of thing. And there's a lot of competitive advantage to be had within that.
I'm sort of thinking of, the kind of wedge, right? Like we have to focus on the sharp end of the wedge where the most kind of high compute, most advanced development is happening. But we also need to think about the rest of the wedge, which is some of the broader applications, the more accessible use, the GPU on every researcher's desk, or the correct number of GPUs depending on what research they're doing, as you make the correct point, Deval. We have a few questions from our audience, so I'd love to turn to those. And there's actually one which I think is a really lovely question, which is, as a generative AI user and data scientist, are there any specific actions I can take right now to mitigate my energy usage in my work? It would be great to have the energy ratings which were mentioned, but are there other obvious tips and tricks that they should be thinking about? Which I think is a lovely question and really brings this conversation back to the level of people doing work at their computers. So I'm curious if any of you have thoughts on that.
I think that measuring, I mean, I guess it depends on level of technicity, but using a tool like CodeCarbon or others to measure the electricity usage, switching to, I mean, for example, if you use Google Cloud or Azure, one of the cloud compute providers, you can switch to places that are low carbon or powered by renewable energy. I think that they started showing that, which is great. Also kind of thinking about what kind of model you need for what task. Like a task-specific models work really well for a lot of cases. I mean, there are some cases when you need to do absolutely everything, but it's pretty rare. So, for example, if you're doing, I don't know, whatever, web search or information retrieval, right? Like a model that does specifically information retrieval can work quite well, as opposed to a model that does a bunch of other tasks. Yeah, that's like off the top of my head. That's all I can think of.
Yeah. I'd be curious for others' thoughts as well, but Sasha, can I ask? Actually, I want to ask all of your thoughts on one thing as well, which is the kind of models that are optimized for certain tasks. Do we see a trend that we're going to see more of those, or I'm curious because I think we're seeing a trend towards looking at how we can make models more efficient, and one of those is task optimization, right? How is that kind of comparing with models that are more general purpose, applied to a range of ways? What are your predictions of trends in that space in terms of how much model optimization we're going to see across the board?
I think Sarah's well placed to answer that question.
That's true.
No, go for it. Go for it. I'm happy to weigh in afterwards.
Okay. I think we're starting to see more. I mean, I think for the longest time we were really pursuing general purposeness. But nowadays, like there's more reflection about, especially, I mean, I think that it's kind of like it's kind of waves, I guess. So I think that there's still going to be this pursuit of multiple tasks at once. I don't know if general purpose is really a thing, but at least like models that can do multiple tasks, but not necessarily for all uses. So we're going to see a little bit more specialization, especially for industry, like for people who like SMEs, and like you don't need a model that does absolutely everything just for like a chatbot that answers customers' questions, right? So I think that we are seeing a little bit of focus, a little bit more focus on efficiency and specificity.
Can I offer a wild guess? And I, to be clear, unlike some of the folks here, I don't really develop models on the day-to-day. But one of the trends I've observed that I think Sarah was alluding to in the need for really high-end compute, it does take a lot of compute to push the frontiers of what's possible, right? And I don't think there's any debate about that. And what that exposes us to is what you can do. Right. And then I think it's maybe the natural trend, and this is a question for everyone here, is it that, hey, we get with brute force to a new level of possibility, and then we come through and we say, all right, what did we do that was inefficient? How do we actually, think about like which data do we want cleverly to really optimize the whole training process? And then you come behind with sort of the more efficient things. Or, maybe we actually see more progress on the hyper specialized models. I'm actually kind of curious in this. My intuition is it's maybe the brute force followed by the elegance, but that's a good question.
And maybe I'll quickly ask as we'll get back to the questions and Aidan can. I agree with what Sasha and I think you were saying. So typically the strongest models, highest performance, generally you end up pushing a lot of compute to figure it out, but then you can distill a lot of things. And I totally agree with Sasha. I think when you talk to people about what they care about, they typically care about their 3 use cases. And there you have a lot of what's interesting is how do you adapt these general purpose models efficiently to target those use cases. And sometimes you can get away with a much smaller model if it's very tailored. A lot of times it's still more performant to kind of steer a larger model. But I actually think that's really promising, right? Like, how do we go smaller and more tailored at the same time? But yeah, I think there has been a wave. We're really excited by general purpose, but now we're also really excited about specialization, which is returning to this idea of how does it work. But Aidan, I'll go back to you because I think we have a pile of questions now.
We do, and
I-
we're gonna get through them. But
I'll just quickly before I'll just quickly add, like, in all of the scenarios, I agree with all of them, but I do think we have already entered the G1's paradox, where even like the building smaller models and training smaller models and doing all of these things becomes cheaper, the more people will do that. Like, so this does not, I don't think this does negate the need for more energy for more compute, which will still manifest, right? Even if we say stop building large models like today, like,
there's the kind of points that are made in many fields, machine learning, but elsewhere, that actually efficiency increases overall usage because more people can use the thing now that you've made it more efficient. So I think you're right to bring that point up. There's a couple of questions that I'm going to tie together with a meta question around kind of what should policymakers be thinking about. So we have one question around, could something like universal basic compute, which is an interesting concept, be a policy here? And then we have another question around what strategies can be implemented to mitigate the lack of access to these resources for especially marginalized students and people around the world who don't have access to these resources. So those are 2 specific questions, which I welcome comments on, but I think the more broad question there is, if for folks working in policy, governance, strategic settings, what should they be thinking about to help address some of these problems? Sasha, I know you've done a policy primer recently, so I might put you on the spot for this one.
Yeah, I'm thinking, I guess it really depends on what level folks are at, right? I think that so it's really dependent on like what's accessible to you. What we talked about in the primer that I thought we tried to cover a lot of ground, maybe failed, but anyways, it's talking about like there's technical things that you can do as like a technical developer. You can work on, distillation, like specialized models, but there's also kind of behavioral things like choosing models that are already trained based on their efficiency, or taking this into account, because I know that of course there's performance and there's all sorts of things, robustness, right? So efficiency is never going to be the only criteria, but just taking this into account when making decisions and like promoting that within an org, saying that, okay, great, like, I mean, performance is definitely important, but let's try to find a trade-off or between these 2 things. And also, I mean, as I said, like choosing the, like, I mean, for example, if you're trying to build a compute cluster, like we talked about, trying to allocate, I mean, trying to put it in a place that's powered by renewable energy is a big one. And in terms of like policy, like high level policy, I mean, I think that we're starting to see some interventions that will hopefully give more access to people. But I mean, I think it's going to take time to develop any kind of regulation. And I mean, we'll see how things get implemented in real life.
Thanks, Sasha. Deval, there's a very specific question in the Q&A that I was wondering if you wouldn't mind either answering live or typing it.
Yeah.
So someone's picked up on the you mentioned, data centers in the Middle East and sub-Saharan Africa, because of the solar potential there can reduce greenhouse gas emissions. How does that work with cooling in those regions, which are obviously a lot warmer than some other places where we find data centers.
Yeah, so I think I read the question, and I think the real challenge is actually water, like versus electricity. So there is a huge potential for abundant like renewable electricity, and when you combine that with say battery storage, and we didn't touch on it at all, but like battery storage per megawatt hour is decreasing by orders of magnitude like every single year, right? And so batteries are becoming cheaper and cheaper, and so to deploy those batteries will be like will become more cheaper, right? Water is a challenge, but then I would challenge that, we have moved away from large like infrastructure where everything is moving towards like water cooled. We should critically assess it, like it is because we are putting these data centers in a region where you can have this water cooled systems. Maybe we don't need all of those water cooled systems, right? And then a good thing about this is a lot of those region has huge access to water, just not drinking water, right? So they have large coastlines, and so there are like methodologies where you can utilize some of that. Like it is, I don't want to like diminish the challenge of water for sure. From my perspective, HVAC is not a challenge actually, like because we have systems, and you have to just that's where 1/3 of like data center energy costs come from, is not actually running like chips, but actually running HVAC systems. And so we can tackle that. Like water for me is like a bigger challenge. And Aiden, I just say like, on a previous question, I know it's not directly the question, but I'll say I have an opinion on what we should not do from policy perspective, and which is on like the energy side of things. Like, we have made tremendous progress even in terms of policy to expedite this transition to renewable energy. The last thing we want is to meet this demand to start building coal and gas fired power plants. And so we shouldn't go back on that actually, because once you start doing that, that's a 30-year infrastructure, right? And so you are not just doing it once, but you are putting our entire like transition plan delayed by 30 years is something to think about. So from a policy perspective, I would say there are other mechanisms. There are market mechanisms like energy markets, like CAISO, like California Energy Market is like introducing like new measures for grid stability. All of those are great, but the last thing we want to do is go back on policies which will enable building gas and coal power plants.
Mhm. Thanks, Deval. We're running up against time, so I'm going to wrap up soon. But there's one question that I think is really important that we answer. And Sarah, I might throw it your way if that's okay, which is what strategies can be implemented to retain talented grassroots computing researchers who feel marginalized, including women in regions like Africa?
Oh,
So on a tangent, but it's a really nice question and one I think we should cover.
yeah, I mean, I think this is related in terms of what Deval was saying about we're talking about efficiency and use of energy, but also ultimately it depends on technical capacity. It's the same thing as releasing weights. It's not sufficient itself. You need to have an ecosystem around it to allow for breakthroughs to happen all over the world. I would say open science communities are a very important first way to get exposure. So I would recommend MLC, Masakani. We have the Cohere for AI community. Hugging Face has a Discord, which has a really active community as well. And these are ways in which you can at least meet people who are doing research and start to get exposure. Ultimately, I think that there's programs where you want to connect with researchers for more intensive training. So we have our scholars program, but I think there's also I think that part of it is also finding regional programs. So in this case, Kipu is also a good example for Latin America. What I will say is that the journey is still very lonely for people who come from certain parts of the world. And so I think that these programs are operating as a reference point, but in many ways, it's still formidable hurdles for people who come from different regions of the world, and we need to change that. So it's perhaps deserves its own panel.
I was just thinking the same thing, Sarah. I think we have a future topic sorted. Yeah.
Yeah, but really lovely. Thanks, Aidan.
Yeah, well, that brings us right up to time. I'm so grateful to all four of you. This has been one of the most fun ones of these for me that we've done. This has been absolutely fascinating. I'm grateful for your time. I'm grateful for your thoughts and for all the great work that you do. I was gonna ask for like one final thought, but we're a minute over and people have other calls and things to go to. So I will say thank you so much, and please keep in touch. Look forward to seeing all the rest of your work that you do. Thanks, everyone.
Thanks, everyone.
Thanks.